periods and the ontogenetic shape of behavioral plasticity. And this is work done in collaboration with Kim Hoke, Andy Barron, Mark Halber, and Michael Koch. And it came out of a working group at the National Evolutionary Center, where folks were really interested in thinking about the effect of learning and experience on phenotypic plasticity, with sort of a specific focus on critical or sensitive periods. So if you've ever had to teach or watch someone learn how to play a video game, you've noticed that that experience is quite different depending on the age of the individuals, where young people seem to take to it with a ferocity that just isn't quite the same as with older folks. And so this sort of brings up this general notion that there are some sort of traits or abilities that are sort of more plastic or easier to acquire in individuals who are younger than when they're older. So this kind of motivates a more general question about how do these kinds of sensitive or critical periods evolve, and more specifically, what are the evolutionary, ecological, and physiological forces that shape or constrain patterns in age-dependent behavioral plasticity? So if we want to think about, sort of talk a little bit about generally what we mean by phenotypic plasticity, it's something that is really crucial for thinking about variation in the environment. So we've got some kind of variation along some kind of environmental axis, and the phenotype then can respond to that variation in some way. And what this variation then implies is there's not going to be one max, only one peak for fitness. So the kind of phenotype that organisms are going to want to choose in terms of maximizing the reproductive output will depend on that environmental state. So what we sort of plotted here is this idea that there's some kind of environmental tolerance curve where we map what the fitness of an individual at a given phenotype is as a function of the environment. And on the other axis here are a set of reaction norms, and those are just how the phenotype of the individual, so whether it's constant as a function of the environment here with this red line, or whether it's a sort of a shallow straight line as a function of the environment with this blue line, or it's a steep line as a function of the environment with this green line. And depending on what the shape of the fitness is a function of phenotype and environment, some of these reaction norms can be better than others in terms of allowing organisms to have a high fitness across a whole range of environments. So we can sort of categorize these different reaction norms in different ways. The one that doesn't respond to the environment, we can think of as a specialist. The ones that respond to the environment either sort of shallowly or strongly, we can think of as generalists. And this one here that has the highest fitness, the max fitness in all possible environments, we can think of as, sometimes we call it Darwinian demon, the individual who maximizes fitness across all contexts. So it's the gray goose scenario. And so while that's kind of interesting, the reason that's an interesting endpoint or sort of boundary case to look at is that's the kind of most maximally plastic organism we can think of, and why don't we have those kinds of organisms floating around, invading the planets or making everything look gray all over. And so the reason that in general we think of that doesn't happen from a conceptual level is that it probably takes, it takes some amount of investment or physiological resource to produce a certain phenotype, and then that investment may have to be repeated over and over again to produce those phenotypes in alternative environments as max phenotypes, these different reaction norms. So ultimately there's likely going to be some kind of biological cost or biological constraint that limits the production of plasticity, and this is ultimately then the source of the kind of diversity of different strategies that organisms use to adapt to variable environments. So when we think of these kinds of costs and constraints, they can include lots of things. They can include a lack of the appropriate genetic variation to produce the phenotypes that are necessary in a specific environment. They can include genetic correlations among those traits that are responsible for important phenotypes in different environments. We could have life history trade-offs, so there could be a finite set of resources among which we have to choose whether we invest those resources in survival or producing new offspring. There could be developmental constraints, so time at which we assay the environment to figure out what state it's in. It might take some time to build a phenotype so that it's properly fit for that environment, but by the time that phenotype is built, the environment has already moved on and changed to something else. Or there might in fact be an issue with the reliability of the cues that we're getting from the environment in terms of being able to sense what state the environment is in order to produce an appropriate phenotype for it. So in general, while these cost constraints are super important, it's actually been sort of an interesting trend in the field that they've been very hard to nail down in terms of attaching particular cost constraints to to particular phenotypically plastic traits. So that's part of the motivation of some of this work, is to try to make the theory a little bit more detailed, a little bit more appropriate, so that we can maybe start to attach specific costs and constraints to particular plastic traits. So the kind of plasticity we're thinking of here more broadly is this age-dependent plasticity that we're calling a sensitive period. So really any kind of age-dependent plasticity that has a sharp decline at some later age. So this could include these kinds of classic examples like critical periods in song learning, where there's some period of time early on in the organism's life where it's sensitive to a template or to a model individual, at which point, and then at some later point, that sensitivity shuts off abruptly, and then the animal doesn't have for any further opportunity to learn new songs or learn from new templates. But it could also include things like imprinting or nestmate recognition, where individuals are sort of at an early stage of their life, they look around for this reliable information about who's their kin or who's their parent, and then they imprint on that so that at later points they can recognize their kin. So to build, what we were in part interested in is sort of building a better baseline understanding for how this kind of age-dependent plasticity could evolve. So really, in order to understand the forces shaping this kind of plasticity, we need to have a proper accounting of the effect of life history on plasticity. And so specifically, we need to be able to account for the effect of aging and senescence on the evolution of age-dependent plasticity. It's surprising that that's something that's not been discussed almost at all, at least in the theoretical and the conceptual work that's been done on age-dependent plasticity. There's no sort of really sort of proper conceptual grounding in terms of what are the effects of life history on these traits. And so the baseline model that we're proposing is one where the level of adaptive plasticity should decline with age, essentially due to the effect of senescence and due to the effect of this declining force of selection as individuals get older. So really, this kind of model just borrows directly from evolutionary theory for senescence, which was something developed from ideas from Peter Medawar, George Williams, and Bill Hamilton. And so the idea here was that as long as organisms are experiencing some kind of constant mortality over their lifetime, that as they get older and older, there will be fewer of them around, and there will be fewer opportunities for selection to act on traits that are expressed in individuals who are older. So what that allows you to do is it allows you to plot curves which sort of show you the force of selection on traits that might affect survival and the force of selection on traits that might affect fertility. And so we can imagine then that if we're thinking about adaptive plasticity, that those traits that are adaptive plastic traits that affect either of those two components of fitness will have stronger selection on them in early life. And so then there's sort of the nice thing about exporting this kind of theory to this topic is that there's very well-defined expressions for these kinds of things, for the force of selection on fertility and on mortality. And so what we can do is we can use these kinds of ideas to compare different kinds of life history schedules to see what the effect of those schedules have on the force of selection over the organism's life, how that might affect then evolution for or against a kind of critical period. So for example, we could take a pattern of increasing mortality with age and compare it against a pattern of decreasing mortality with age, and then see what kinds of curves for the force of selection on fertility and survival those things produce, and compare them to the pattern of age-dependent plasticity that we see. So for example, we might think that because here that the force of selection is strong over the whole course of time, that critical period is acting, that the closure of this might actually be selective, might have a selective basis that's not connected with some kind of effective senescence. But whereas here the force of selection is decaying strongly around the time of the critical period begins to decay, that it may not be as clear that the senescence effects aren't actually something that could be important in the closure of this critical period. So to show that this works sort of not just in sort of conceptual theory, but it works quantitatively, I'll present some very preliminary simulation results that I've done the last couple of weeks. The model feature of senescence called mutation accumulation. So the idea here is that mutations, there are going to be some kind of deleterious mutations that are happening at a constant rate, and those mutations are removed from the population by purifying selection. And that selection, that force of selection gets weaker as organisms age. So at some point, you just get sort of a sort of baseline accumulation of deleterious mutations, and that's what's causing the deterioration in traits that generate positive effects on, positive effects on survival. So we'll do this by borrowing a model from Russ Landy from a recent paper in the Journal of Evolutionary Biology, where he looked at phenotypic plasticity using a linear reaction norm. So this just means that the phenotype is a straight line function of the environment. So the environment is multiplied by some slope that has a genetic basis, and then some intercept that has a genetic basis. It's just a straight line here. And then we assume that the optimal reaction norm is also linear, and there's some parameters sort of given by the environment. There's some parameters, an optimal slope and an optimal intercept. And then just assume that fitness is some kind of Gaussian function where individuals have the highest fitness whenever they're at a phenotype that have a reaction norm that's exactly the optimal reaction norm. And as well, we allow for there to be some kind of cost to plasticity, so a cost to this slope, this responsiveness to the environment. So this sort of generates, this fitness function generates this environmental tolerance curve here. And this is, again, that same plot of these different kinds of linear reaction norms. So these two important parameters will be the strength of selection here on the optimizing for being in the optimal reaction norm, and then whether there's any kind of cost of plasticity. So what we'll do to change this model is we'll just add age structure. So we'll allow each of these phenotypes to have an age-dependent value, and each of these genetic traits to be expressed as specific ages. And as well, then, the fitness components could be either components of fertility or components of survival. So this is just to give an example. This is a specific life history schedule that I chose. So this is the mortality curve. So it's increasing mortality with age. And then these two curves are the force of selection. First here, this dotted line on survival, and then the solid line on fertility. And so here, the crucial part is the optimal reaction norm has a slope of 2 and a intercept of 2. And here, there's going to be no cost of plasticity. First, we'll look at when traits have an effect on fertility. And what we find is that for early age classes, we evolve the optimal intercept value and the optimal slope. So we have the optimal reaction norm. And then finally, for very late age classes, the last age class where the force of selection is weak, we see that there's a reduction in the ability to get towards that optimal. In fact, we're wandering around about 0, which is that mutation accumulation result, where there's no selection, we're just getting deleterious mutations. If we then increase and allow for some kind of cost of plasticity, we see that there's sort of more variance now at the intercept, and that we've reduced our ability to evolve towards that optimal slope of 2, and in fact, we're even below the value of the level of plasticity that we would evolve, that we would predict even from the Landy's original model, which didn't have any age structure in it. Next, we can look at the effect of now classic traits instead of affecting fertility, they affect survival. And we see there's sort of a general pattern where there's even weaker selection now on the involving the optimal norm in terms of the slope of the intercept. There still is this pattern where those values, selection of those values is stronger for lower age classes than it is for later age classes. And then finally, if we allow for this cost of plasticity in this case of survival, we actually don't get even any evolution of the slope parameter at selection, so we get some evolution of this intercept parameter. So just to conclude, life history is a crucial factor when thinking about the evolution of age-dependent phenotypic plasticity. The closure of these kinds of sensitive periods, things that we might think are being important for things like song learning, should be shaped both by selection for the benefits of the traits that are used in those sensitive periods, as well as senescence of those plastic traits as individuals age. And the plastic traits may evolve differently due to senescence, depending on whether traits have primarily affect survival or affect reproduction. And with that, I'll take a question.